Well, people have a tendency to do, to make a mistake. There's a common mistake that I wanted to warn you against.
I probably made the same mistake.
I only got one step.
Here, let's go. Let's bring up the theorems that you're supposed to prove. Okay. Now let me see which one. So let's take them in order. What was the first one that you had a question on?
14.4.
So we're trying to prove 14.4 membership. Okay. Now, yeah. So let's take a look at 14.4. It's here. It is theorems for cross product. It's membership, and it's xy is an element of s cross t. Equivales x is an element of s, and y is an element of t. So what I recommend you do is you start with the left-hand side. And now, here's the thing. What you should do right away is use the definition of S cross T. And the definition of S cross T is given in 14.3, right? So now what you get is something like this. You get that x, y is an element of, and then you have this set, only instead of having a set over just B, you have a set over BC, and then range da 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 da, right? Is everybody with me on this? This is what you're going to get as you're going to get x, y as an element of this set. Now here's what you need to do. What you do here is you go back to 11.3. So let's go back to 11.3.
Is that set membership?
It is set membership, but the thing about the set membership is
You consider the
let's
as one unit, right?
let's look at this. Let's look at this set membership. This set membership says F is an element of this set X, and that equivales there exists an X, right? But the thing of it is that you understand that whenever we have a dummy variable, this X in there exists an X can be a list of variables. All right? So here what this is, instead of having X, what do we have? We have B comma C. So whenever we switch, maybe this is what your question was. Whenever you make this go to an existential, well, it's legal to have an existential like there exists a B and a C. I mean, see, we do this all the time.
Mm-hmm. And then in the body, that's where you have BC equals XY.
Yeah.
Yeah, and then in the body, yes.
I didn't know we kept the variables BC, so I changed them to XY. And that's
No. Oh yeah, I noticed you said xy equals xy. No. Yeah. I noticed in your email, but yeah, and I'm sorry I didn't have time to reply to it. I was really busy over the weekend, but I kept saying to myself, I need to answer your email, and I just never did get a chance to do it. Well, that's why I'm letting you have an extra day. Okay, so anyway, are we good? Okay, but now, what do you think you should do?
This is where I was more confused. Do you use the pair equality?
Well, not yet. I mean, not yet.
That's what I did.
Not yet. I wouldn't do that yet. I mean, it's a little cleaner. No, it's okay. It's okay to do that, but I would not do. Actually, no, I wouldn't do that. I wouldn't do that at all. In fact.
Can you do the double trading?
Yes.
Oh, see, that's what I did after that.
No, you should do it before that, because if you do it before that, if you do double trading right away, existential double trading right away, guess what you can do? You can use the what?
1.0.
Which 1-point rule?
There was only one. Wait. No.
There's two?
There's
The one with
two.
There's what?
Higher quality one.
The order, you can use the,
Yeah, one.
yeah. See?
Yeah.
You can use 14.2.1, which is the ordered pair.
What is it?
That's the ordered pair 1 point. You proved it. You proved that. But see, the slick thing about doing it is that here you've got the ordered pair in the range.
And that ends it right there.
And that ends it right there. You don't have to reinvent the ordered pair one. Otherwise, you'd have to do nesting, blah, blah, blah. And
I did that proof again.
in essence, yeah, if you do it that way, in essence, what you're doing is you're kind of like reproving the ordered pair 1 point rule in your proof.
Yeah.
But you can just take advantage of that. That's why we have the ordered pair 1 point rule. Now, is that cool? Now you have to admit that is cool.
It's really not that cool, but interesting maybe.
Okay, so is that a good hint? How's that? Okay, now I also want to give you a hint about 14.15.3. Now, with 14.15.3, you have to be very careful because what you should do is you should start with the left. So let's look at 14.15.3. You're starting with x comma y. You know, ordered pair xy is an element of I sub b, right? And we want to show that that equivalves x equals y. Okay, start with the left-hand side, right? Now, obviously, the very first thing you're going to have to do is what? No.
I did 14, 15.
I did 14.4.
No. X.
Are we doing 14.5?
We are talking about proving 14.15.3, okay? And I'm saying start with the left-hand side.
Do you want to do
14.15.
membership?
Yes. The very first thing you should do is 14.15.2. But look, this is where this is where a lot of people go wrong. If you say this, if you say x comma y is an element of,
Please don't say it.
if you say x comma y is an element of the set x range, hold on, or is that x
Boolean.
type Boolean?
Type
Okay,
Boolean.
okay, well, okay, that's just type. What?
Range.
No. X. No, it's not Boolean, it's B. Yeah, this B is not Boolean. See, Boolean would be this.
X.
Here, Boolean looks like this, so that's not Boolean. But it's X type B, and what is the type B? Type B is the set on which the relation is defined.
Okay.
All right?
I sub B, right.
Yeah, so I sub B. But anyway, and then range what?
True.
Range true, but then what do we have here?
XX.
X. All right, do you guys know what question I'm going to ask you now? Is this X bound or free? Did I hear a free somewhere? No, okay, you're just not. It is bound to this. Is this X bound or free?
That one's free.
That one's free. So my question is, therefore, is this X the same as this X?
No.
Absolutely not. So what had you better do?
Change it.
You had better not call this one X. Because if you just go willy-nilly and move this in there, you got two different X's and they're called the same thing, and you can't do that. And that would be bad. That would be bad, bad, bad. So instead of writing it like this, how do you write it? How do you write it? X comma Y is an element of what?
Okay. Q.
Well,
Q.
how about Z?
Z.
Well, X, Y,
Who
Z.
does that?
X, Y, Z, you know.
It's far too related.
Yeah, I'm still gonna do it.
So you had better do it, if you do it this way, it's wrong. If you do it this way and you bring that in, I mean by a set, it would be wrong. But if you do it this way, you have to do it this way because you have to use dummy renaming.
But you said that online. Can we get a note here?
Oh, yeah, I did say this online, but I didn't actually write it out. Yeah, so now it's written out.
So after
Now on this one, it is good. Now, on this one, you should use pair equality, because you have an existential, right, with just one variable here.
So you would use the membership and then equality.
Well, use 11.3. Yeah, set membership and then use pair equality. And then what you can do is you can trade one, because you have an and with an existential. Do you remember how you can trade within?
You can just put it onto the body. Or
You can trade, yeah. You can trade and then eventually you can get it to a 1 point rule.
Do we not need to deal with the fact that Z is of set B?
No, that doesn't really enter in, so you can just.
I tried to put that-
keep it there or
I
not.
tried to change it so that was in the range. Like,
No. That's the B. The B is just an annotation for what, as a reminder of what the type is. So that does the B. The big B doesn't enter into any of the calculations. You can just drop it.
So you want to get something into your arrangement? Does it matter which one?
I
you want us to trade in
just
1.0?
try. Well, just try it.
What are we trading?
What I'm saying is, you have range true here. If you
Yeah.
trade and get one of those terms into the thing, and then you can investigate that.
X, Y,
This?
yeah.
Was that? What's your question about that? Is this what? Did I ask you to prove 14.5?
Yeah.
Okay. So what's your question?
Well, I started with the left-hand side.
Yeah, that's what you should do.
Start with
And
what?
then
Start with the left-hand side.
should you use 14.4 or should you just the I don't know which one it is 14 or should you use the cross product?
Both?
Well, what?
Because doing 14.4 got me kind of nowhere.
Why did it get you nowhere? That's exactly
Because I have X is an element of S and Y is an element
okay.
Symmetry.
And then what? What are you trying to get it to?
that YX is an element.
Yeah. So how do you make it look more like what you're going towards?
If you just do symmetry and then do it backwards.
Yeah. Use symmetry and then use 14.4 with what?
X, Y.
Replaced by YX, which is, if you want to write it out, you can see it.
When I did that proof, I was like, I probably did this wrong.
That's why I was like,
It's
why
so
did you
simple.
change
It's
that?
like, look out for that.
you don't. Is that? Are you asking me to not assign simple problems so that you can get
We
some?
need these simple problems for theory and then just to understand building blocks if you want.
Oh, whoa! Listen to this supporter over here.
Just one of your problems.
Baby steps, right? Okay,
To class.
how we doing? Is everybody good? And then we can you can have a little extra time for that.
The final grade you put in the exam book is our current grade in the class.
Exactly, as usual. All right. Now, so today we want to continue on our discussion of relations. And 14, we did 14.15. And last time we talked about, we got all the way down to 14.15. We did binary definition of a binary relation. The identity relation, we looked at that, at that definition. And 14.15.3, you're approving for me, and you can now give that to me tomorrow. And I think the next thing that we wanted to look at is 14.15.4 and 14.15.5. Now, we have to get used to some notation here. So let's take a look at 14.15.4. B comma C is an element of row, and B row C are interchangeable notations. So do you remember when we had, what was the example? If S is 0, 1, 2, if S equals the set 0, 1, 2, and then we said the less than relation was what set? What was the less than relation? Do you remember over S?
0, 1, 0, 2.
Yeah, it was zero, ordered pair, exactly. Ordered pair 0, 1, ordered pair 0, 2, ordered pair what? 1, 2, right? Are you with me?
Sure.
Okay, now let's take a look at an example of 14.15.4. What this is saying is that B comma C is an element of row. Now, that's, oh, by the way, this letter is Greek letter rho. This letter is English letter P. So let's make sure that we, all right, that we write it and say it, you know, with the distinction. Because it's all the, you know, alpha, beta, gamma, delta, come on. We ought to be, that's our heritage. That's our, you know, before the Latin alphabet was the Greek, you know, alphabet, you know, okay? So anyway, now, so what does 14.15.4 say? It says this, for example, it says that ordered pair 0, 2, now get this, is an element of less than. Look at here, you guys. Ordered pair 0, 2 is an element of less than. What is less than? What is the less than relation? It equals this what? This set. And what is a set of? It's a set of what kind of things? Ordered pairs. And so this ordered pair is in that set of ordered pairs. Are you with me? Is everybody clear on this? 0, 2 is an element of this set. This is the same as, and here what it says, and what? Now, what is it saying? What is this B, rho, C in this example?
0,
Not comma.
row 2.
But what's our rho in this
0
case?
less than 2.
0 less than 2. Look, does it, yeah. Does everybody understand, does everybody understand what I wrote? No, it's not dumb. Rho is a symbol for an arbitrary relation. And this is an example of a specific relation. Are you with me? And so in this case, what it's saying is that the ordered pair 0, 2 is an element of this relation, and 0 is less than 2 are what? Interchangeable notations. Are interchangeable notations. Now, does everybody see how that works? So sometimes you're going to use, sometimes when you prove a theorem, sometimes we use this notation, and sometimes we use this notation. And you have to be able to switch back and forth. Yeah? So just to make it explicit, I put it up there as a separate thing, interchangeable notation. Right? Now let's take a look at 14.15.5. Conjunctive meaning. Now, what in the world is this? What we're saying, what 14.15.5 says, B, rho, C, sigma, D. Now here's our convention. Our convention is that these lowercase Greek letters represent what? Relations. They are symbols, but they represent relations. Whereas the B and the C and the D are elements of this S. They're elements. They're not ordered pairs. Are you with me? Sure. So what this is saying is that B, rho, C, sigma, D, by the conjunctive meaning is what?
0.
It's B, rho, C. And then what does it say? 14.15.5. And C, sigma, D. Now what is that saying? What this is saying is that 0 is less than 1 is less than 2. In this example is what?
B is an element.
It is 0 is less than 1 and 1 is less than 2. So we've seen this conjunctive meaning before. Are you with me? But this is just the same thing in general. So now you're going to have to you're going to have to start thinking in general, but if you want to relate it back to something specific, think of it like this. Are we good? Okay, so that's the conjunctional meaning. Now there's one more thing that I want to point out, and this particular representation is not in this chapter of the book. And I want to show you what is called the matrix representation. Because this is going to help. I'm going to have a study sheet for you that uses the matrix representation to illustrate the properties of relations. And here's the way the matrix representation works. Again, if this less than relation is the set of ordered pairs 0, 1, 1, 2, and 0, 1, 0, 2, and 1, 2.
Does it matter what order they're in?
It doesn't. You knew that.
I know, I'm just making sure.
I know. Okay, now here's the matrix representation. The matrix representation, now, oh, by the way, you remember what the graph representation is? Remember what the graph representation was?
Three circles and then-
Yeah, it was this, 0, 1, and 2. And from 0 to 1 is from here, from 0 to 2 is here, and from 1 to 2 is here. So this is the graphic representation. The matrix representation looks like this. What you do is you have however many elements there are in S, you have a matrix with that many rows and that many columns. Are you with me?
All right.
So here we have this matrix, and we have 0, 1, 2 here, and 0, 1, 2 here. And what happens is, inside the matrix, anytime you have a ordered pair, from X to Y, you have a 1 in the matrix. And if you don't have it, you put a 0. So what this matrix would look like is this. It would look like this: 0, 1, 1, 0, 0, 1, and 0, 0, 0. Now, does everybody see why that is? Can you hand me that blue marker? See, look, this, let me, yeah, the row first, yeah. So this 1 in column 1, row 2, this 1 in column 1, row 2 means that ordered pair 1, 2 is in the relation. Okay, now does everybody see how that works?
Is that column 1?
Yeah, this is, sorry, row,
Is it column 3 or column 1?
wait,
Row 2, column
row, it's row 1, column 2.
3.
0, 1, 0, 1, 2.
That's row 2.
This is the column.
Are you doing by the numbers or by the
Oh.
actual rows?
0, 1, 2, 0, 1, 2. I did not say second row. I said row 2.
Goodbye.
How does that,
Right?
how is it column 1?
Because there's,
He's saying it's
0, 1.
second column. He's saying
Is that-
column 1.
Oh, wait. Whoa. No wonder.
Column 2.
yeah,
Row 1, column 2.
rows are horizontal.
No, it wasn't crazy.
Did I do my... Oh, my notes are wrong.
Standard. Standard.
Putting a video
What are we doing? Good math.
Shoot.
Nice one.
I stand corrected.
Matrix goes a bit. You do.
Have you used this in other classes before? No.
In this class.
Last year?
Well, this is a new, I have slightly new notes. I just, yeah.
It's like,
Yeah.
no one has.
No one last year caught that. Slightly new notes. I'm introducing this now. At this point.
We're the first year to get to see this stuff.
Just this one particular erroneous note. All right. Are we good?
Yeah, actually. What row do again?
All right. Now let's get to 1416 and 1417, which are the definition of domain and range. Okay? Now, I want to draw some pictures for you here. So 14.16 defines the domain, and it's DOM dot row. So DOM is it's like a function, and row is the parameter of the function, right? And row is a relation, okay? And what it's defined to be is the set of B in big B range, there exists a C, range true, such that B row C. All right? And the range of row is defined similarly, except for the fact that it's the set of all C's in range there exists a B, in range that there exists a B, range true B row C. Now what in the heck does that mean? So let's do 1416 and 1417.
The definitions.
So are these like type B then?
Yes, those are the big B and the big C are types, and I want to give you an example. I think that I hope will make it clear. All right, so let's suppose we have these two sets. Suppose we have big B is the set 2, 3, 4, 5, and big C is the set 4, 5, 6, 7. Okay? And we are going to define, so these are our sets, right? And we are going to define a relation called pred. And pred stands for predecessor. Okay? So define, so here we're going to define predecessor relation. Define predecessor relation, and we're going to call it B pred C over B cross C. Now remember, this is the, what is this? Cross product? What is this? What is the set B cross C? Can you tell me how many elements are in B cross C?
53.
Nope.
Close.
Nope, not even close.
16.
16. How'd you get that?
4 times 4.
4 times 4. And what is it a set of?
Order pair.
Ordered pairs. And what are the ordered pairs? 2, 4, 2, 5, 2, 6, 2, 7.
Yeah.
3, 4, 3, 5, 3, 6, 3, 7. 4, 4, 4, 5, 4, 6, 4, 7. Is everybody clear on this now? Right? Are we good? See a few puzzled faces out there. Okay, so we're going to define the predecessor relation over B. And what is a relation? It is a what?
List of variables with values.
No. No, what is a relation?
Subset.
It's a subset of that set.
Sure.
And what do you suppose that pred, so what do you suppose, how do you suppose we should define pred? Pred equals, now when I write this equal, here. When I write this equals, what's the first symbol that we write down?
Curly brace.
Curly brace, because it's a set, but it's a set of what? Ordered pairs. So the next thing has to be, so what's the first ordered pair in the pred? What precedes what?
4.
Well, 3 is the predecessor of 4, right? I mean, that's the one that comes right before it.
3, 4, 4, 5, 5, 6.
Yes, 3, 4, 4, 5, and 5, 6. Is everybody clear? This is just by definition. And we're just defining this. I made this up just for this example. Now here's how you picture it. Now watch this. What we're going to do is we're going to put the elements of B on the left, and there's 4 of them. And they are 2, 3, 4, and 5. Yeah? So these, and we'll just draw this around here. And this is the set B. So this is a set, and it has these elements in it, kind of like a Venn diagram. You know, we draw it. Okay? And then C, it has elements 4, 5, 6, and 7. So we have 4, 5, 6, and 7. We'll draw those here. 4, 5, 6, and 7. We'll put a circle around this, and this is C, right? And so these are the elements in C, right? C is a set. And furthermore, how will we indicate the pred relation? Well, if we have an ordered pair of 3, 4, what is that? How should we indicate that?
3 or 4.
3, yeah, we'll go from here. So it's a mapping. 3 to 4, 4, 5, so it's a mapping like this. 5, 6, that's a mapping like that. Is everybody?
That's how we draw relations with cross products.
This is how we illustrate this relation. All relations are relations over a cross product. All relations are relations over cross product. All relations are sets of ordered pairs.
Right.
This is yet another way to illustrate this relation. So now, you know, we had the graph way to do it.
Oh,
We had the
last
matrix
time-
way to do it.
Because that last time was S cross.
The last time it was S cross
Right,
S.
yeah.
So now we're going more general. Are you with me? Yeah, good point. That was a good point of clarification. Last time it was S cross S. Does everybody understand this? Okay, now can you tell me now with this? Can you tell me what is DOM dot pred? Here, what is that capital D? Yeah. What is DOM dot pred? What does it equal? It equals a what? What do I have to draw right after this? A brace, not a brace, a curly brace, because it's a set. Now, is this a set of ordered pairs? Yes or no?
Yes. No.
Gotcha. Is it a set of ordered pairs?
That's not. It's 3, 4, 5.
Ah, now how did you get that?
It's just the first.
Because it's the set of all little b's in B such that there exists a what?
A C.
A C such that B is related to C. So it's a set of all these such that there is relation from here. Are you with me? Such that there exists something. So basically what it is, yeah, it is 3, 4, 5. 3, 4, 5. Is everybody clear? And what is range dot pred? Oops. That equals the set 4, 5, 6. Now, so these are not sets of ordered pairs. These are sets of elements. Are you with me? So here, if we were to draw it, so if we were to draw it, this would be this is the domain, and this is the range. All right? Are we good? You guys have actually done domain and range before, I think. Well, I mean, when you did functions, I mean, you remember when you graphed functions?
Yeah, we discussed that.
And you discussed domain and range. It's the same kind of thing. I mean, look, what is here? Like, suppose, let's just real quick. So suppose you have a parabola like this, okay? And here this is x and this is like y, okay? So what's the domain and what's the range?
All real numbers.
The domain is all the x, right?
Right.
But the range is just 0 up to infinity instead of minus infinity to infinity. Yeah.
Cross products aren't symmetrical, are they?
Good point.
You always have to use the first one.
Yes.
First.
Yes, because it's ordered pairs. Ordered pairs. Yeah.
There's 3, 4, it's not 4, 3.
Right. Okay. Now here's the next thing is well, we have the definition of the inverse relation on B cross C. Is the relation defined by inverse? So B cross C is an element of row inverse. Now you understand this does not mean 1 divided by row.
Yeah.
Okay, this is like sine inverse. This is like inverse sine, right, in trig. So BC is an element of row inverse. Equivalence what?
CB.
CB is an element of row. All right?
Wild. Watch out.
Now, because, so let's talk about operations on sets. Well, I'll give you an example of this in a minute. So operations on sets. Oh, sorry, not on, sorry. Operations on, yeah. Okay, how about operations? Okay.
Can we take element of the inverse of any set?
Well, I mean, this defines, yeah, it has to be a relation, yeah. The sets of ordered pairs. Okay, so now, because a row and sigma are sets, you can take, now what can you do with sets? What are some of the things that we did with sets? Set equality. What else did we
We
do?
did a lot of proofs.
Well, what were some of the operations that we could do on sets?
Rule.
Union,
Oh, those ones.
intersection, complement, right? Subset, yeah. Our sets, you can take union, intersection, complement. So here let's do an example. let B equal the set, again, 0, 1, 2. All right? And now what is less than? What do we say less than is what set? What's the less than relation? 0, 1.
Didn't we say the
0,
relation
2.
is, like, are we assuming it's B cross B?
Yes. Whenever I just give one, I mean B cross B. Yeah, that's a good point. In fact, that's how, look, the identity lemma, in fact, let's apply that. The identity lemma 14.50.3, when it says I sub B, it means that it's on B cross B. Yeah.
Those don't say that because they're lazy?
Yeah.
Too much writing?
Yeah. See, they like abbreviations. Okay, now tell me. Okay, now tell me, what is equals? Equals is what set? What's the equals relation?
0, 1, 1, 2, 2.
Yes, because that's the identity, right? 0, 0, 1, 1, or not because, but it is. Okay. And now tell me, what is less than union equals? It's kind of hard to read. Less than union equals. If this is the less, yeah, this is hard to read. You have to. This is this set. This is this set. What is that set? Union that set. What is? You see what I mean? It's kind of hard to read. I don't know how to write
Is
it.
it all of them?
All this stuff.
Well, it's the union. It's the union. It's the union of these. And so, what are the elements in the set?
0, 1, 1, 1.
0, 1.
Everything.
Yeah. 0, 2. 1, 2. 0, 0. 1, 1. 2, 2.
Oh, that's a mess.
No, it's not. It's just a set with 6 elements in it. And furthermore, what relation is this?
True. Less than or okay.
Say it again.
Less than or
It's the less than or equal to relation, which is the less than or equal to relation. So here, this is going to really look funny. Less than union equals less than or equals to. No, this is a relation. It's not equivalent. No. It's not. This is a set equality, right? It's ordered pair. It's a set of ordered pair equality. So this has to be equals, not equivalents. Are you with me? But now, I don't expect you. I mean, I don't think you'll never see this in writing. But it's mathematically it is correct.
So the intersection is the intercept?
How about here? How about one more? How about we do the complement? Do you remember how the complement worked? What was the complement of a set?
Everything is not in.
Exactly. So what is the complement of less than is what set? Well, I mean, what are the elements? If this is the less than, then what are all the elements in B cross B that are not in here?
1, 0, 2, 0.
0, 0, 1, 1, 2, 2.
Yeah, 0, 0,
Or equal to.
0, 0, 1, 1, 2, 2, 1, 0, 2, 1, you say?
It's a 2, 0.
2, 0.
2, 1.
Is that it?
Yeah.
2, 1. Which is what?
Greater than.
Or equal to.
Or equal to.
Exactly.
Which is greater than or equal to. Now let's take a look at the inverse. What is less than inverse? 14.18 example. 14.18 example. Now here, this looks really funny. Less than inverse.
That's greater than.
Let's write down what the ordered pairs are. Less than inverse are what?
Okay,
Because the less than, remember, we're saying the less than is this, yeah? Over here?
Let's say it's a 1 0 2 0.
So you flip them all, yeah.
1 0 2 0 2 1.
1 0 2 0 2 1.
Same as greater than.
1 0. What was the next one?
2 0.
2 0 2 1.
2 0 2 1. Which is greater than. So if you want here, if you wanted to write that out, you would say less than to the negative 1 equals greater than. That looks really weird when you write it like that, but mathematically correct, but anyway. Now, 14.19. Now do you see how to do, now you should be able to do this homework for me. If that's due on Thursday now instead of tomorrow
So
with the other late homeworks.
if you just start with the left-hand side, how do you just start with it? Can you just say by?
You go, we have dome, that's domain. You just go right here. That's, the parentheses and the dot are the same thing, right?
Well, yeah, but it's the inverse of it.
Well, yeah. So you
So you
do
can-
that. So, I mean, one way you might have to attack it,
Attacking is kind of a strong word.
Directly.
well, you go into here, and then once you get it like this, then this B row C, another way is that, another alternate definition of B row C is that BC is an element of, oh wait, where's the notation? Interchangeable notations. You might have to do interchangeable notations. And then once you do interchangeable notations, then you know what this, then you can do this, because you have it in that notation. I think you can do it. All right. Now the next concept, the next big concept, is the concept of a product, a relation product. And I do want to get this,
Finish the class then?
yes. So here's the concept of a product. Because did you know that you can actually multiply two different relations together? So we can have like less than times equals, or we could have
Wait, times or like cross?
product. No, not cross product, relation product. Ah! Okay, now the product is denoted by,
You can multiply
you can
Boolean operators.
no, you operate, no, well, yeah, because operators are relations.
Yeah.
Yeah. So it's denoted by this little circle, okay? That's relation product. Now I want to give you an example. And actually we should see where the definition of a product is. Here, 14.20, let's look at 14.20. Definition product. Ordered pair BD is an element of the product. Does everybody understand? Row circle D is, row is a relation, sigma is a relation, circle is the product. Yeah? So what that equivales is there exists a C.
C is a C.
C is an element of big C, so that's just giving the type of C. Okay? Such that BC is an element of a row and CD is an element of sigma. So it's like C comes like in between it. And I see by the old clock on the wall that we will just have to mull this over in our heads and actually wait till tomorrow before we do the example. Okay? Are we good? That's all, folks.